If you spent any time in the Great Plains during the spring, you learn pretty quickly to respect severe thunderstorms. Back in my 20s and 30s, I spent many Mays traveling across the area, studying and chasing thunderstorms. Like many meteorologists, I was fascinated by tornadoes. But one of the most memorable moments of my career didn't involve a tornado at all. I was riding in a university research van while we tracked a severe thunderstorm. We thought we were in a relatively safe position. Then the rain suddenly stopped. The sky turned an unsettling shade of green, and we began to hear the clink and clunk of hail. Before anyone could react, a softball-sized hailstone came crashing through the window of the van. Fortunately, no one was injured. But staring at that chunk of ice on the floorboard, I remember thinking about how remarkable it was that a thunderstorm could suspend something that large in the air long enough for it to grow. How does a storm create a piece of ice the size of a softball? And what happens to that process when the atmosphere itself begins to change? Today we're going to explore the science of hail, how these destructive ice stones form inside thunderstorms, and what new research is revealing about how a warming climate may be changing where and when some of the world's most severe hailstorms occur. Welcome back to the podcast. I'm Dr. Mack, and this is the Climate Translation. To understand why scientists are interested in how climate change may affect hail, we first need to understand how hail forms in the first place. It all starts inside a thunderstorm. Now, most people think of hail as frozen rain, and while that's not exactly entirely wrong, it doesn't really explain how you end up with a piece of ice the size of a golf ball, a baseball, or, in rare cases, a softball. For that, we need to talk about what's happening inside the storm itself. I often tell my students, you can think of the severe thunderstorm like a giant atmospheric elevator or maybe an escalator. On a hot summer day, the sun heats the ground, and the air near the surface becomes warm and humid. And because warm air is less dense than cooler air, it wants to rise. If the atmosphere is unstable enough, that rising motion can become quite powerful. Meteorologists call the fuel for this process convective available potential energy, or CAPE. You don't have to remember the acronym. Just think of CAPE as the amount of fuel available to launch air upward through the atmosphere. The more heat and moisture available near the surface, the larger that fuel tank can become. And when that fuel tank gets large enough, and the conditions are just right, air can shoot upwards at remarkable speeds. In some severe thunderstorms, those updrafts can exceed 100 miles an hour. Now let's go back to that hailstone. Imagine a tiny raindrop or some kind of particle of matter being carried upward in one of these powerful updrafts. As it rises higher into the storm, temperatures eventually drop below freezing. That raindrop, or the seed, begins to freeze. At that point, gravity begins to pull it back towards the ground. But the updraft, it has other ideas. Instead of falling all the way back to the earth, that tiny ice pellet gets caught in an atmospheric elevator or escalator that begins to push it upward again. As it moves through the storm, it collides with supercooled water droplets, liquid water that exists even though the temperature is below freezing. Those droplets freeze onto the surface of the hailstone, and layer by layer, trip after trip, the hailstone grows larger and larger as it continually falls and then is pushed upward again. If you've ever seen a large hailstone, cut it in half. It'll look a little bit like the cross-section of a tree. You'll see rings and layers that form during repeated journeys up and down through different parts of the storm. And this is where the physics becomes surprisingly simple. The stronger the updraft, the larger the hailstone can become. A small hailstone can be supported by a relatively modest updraft. A baseball-sized hailstone would require a larger one. And that softball-sized stone that came through the window of our research van all those years ago, that required an extraordinarily powerful thunderstorm capable of keeping a chunk of ice suspended long enough to grow that large before gravity finally won. In many ways, hail is a balancing act between two competing forces, gravity trying to pull the ice downward and the storm trying to push it back up. As long as the storm keeps winning, the hailstone keeps growing. But what happens when the environment that those stones form in begins to change? Human-induced climate change is not only affecting temperatures on the ground, it's also changing the dynamics of the upper layers of our atmosphere and the potential energy that's available when thunderstorms form. And that means it can influence the physics of the hail equation in surprising ways. Now, at this point, you might think the connection between climate change and hail would be straightforward. After all, hail is made of ice. So if the atmosphere is getting warmer, shouldn't hail become less common? For years, many people assumed that might be the case, but the reality turns out to be more complicated. That's because hail exists in what we might call a meteorological Goldilocks zone. The conditions need to be just right. Think back to that escalator or elevator we talked about a few moments ago that's going up and down. A hailstone needs a powerful updraft to lift it high into the storm and keep it suspended long enough to grow. A warmer atmosphere can help with that. Warmer air can hold more water vapor, and more water vapor means more fuel for thunderstorms. More fuel means stronger updrafts. At first glance, that sounds like good news for hail. But of course, there's another side to the equation. Remember that hailstones only exist because part of the storm is below freezing. As the atmosphere warms, the altitude, which temperatures reach freezing, begins to move higher into the sky. Meteorologists call this the freezing level. You can think of it as kind of like the storm's ice maker. In a warmer climate, that ice maker is being pushed farther upward. Now our hailstone faces a new problem. Once it leaves the storm, it has a much longer journey through warmer air before it reaches the ground. Small hailstones may melt completely before they ever get there. Others may shrink significantly during their descent. So now we have two competing forces. A warmer atmosphere can create stronger thunderstorms that are capable of growing larger hailstones. But that same warmer atmosphere can make it harder for hail to survive the trip back to the surface. One process favors larger hail, the other favors more melting. And for decades, scientists weren't entirely sure which effect would dominate. That's one reason hail historically has been one of the most difficult severe weather hazards to project in a changing climate. The atmosphere is essentially pulling the system in two different directions at the same time. But thanks to improvements in computing power, satellite observations, and high-resolution climate modeling, researchers are beginning to finally untangle that puzzle. And what they're finding suggests that the answer may not be that hail disappears. Instead, the environment favorable for hail may just be shifting. And in some places, it may be shifting dramatically. If a warmer climate strengthens some parts of the hail-making process while weakening others, what does this mean for the overall picture going forward? The answer that researchers are starting to find is not exactly what people expected. A recent study published in Nature suggests that hail is not simply becoming more common or less common everywhere. Instead, the environment that favors severe hail appears to be shifting. To understand what that means, imagine that hail has a preferred neighborhood. Well, maybe not a physical neighborhood, but a region of the atmosphere where all the ingredients happen to line up just right. You need enough warmth and moisture near the surface to generate those strong updrafts, that cape or fuel we talked about earlier. You need cold enough temperatures higher in the atmosphere to support ice formation, our ice maker. You need enough wind shear that separates warm updrafts from cooler downdrafts and generates some rotation to organize the thunderstorm. And you need all of those ingredients to exist at the same time. Historically, some of the best neighborhoods for hail have existed in places like the Great Plains of the United States, parts of Argentina, South Africa, Europe, and portions of Australia. That's why some of these regions develop reputations as hail hotspots. But new research is suggesting that those neighborhoods are changing. As temperatures continue to rise, many regions closer to the subtropics are projected to see conditions less favorable for frequent hail formation. At the same time, areas farther poleward may begin experiencing more of the atmospheric ingredients that support severe hail. In other words, that sweet spot appears to be moving north. It hasn't been a rapid movement yet, but it's been enough that scientists are beginning to see a constant signal emerge across multiple regions. The researchers are also finding something that's equally important. The changes aren't just geographical, they also may be seasonal. In some regions, the timing of hail favorable conditions may be shifting within the year. That means agricultural areas that have traditionally experienced the highest hail risk during one part of the growing season could see it arrive earlier or later than expected. That matters because timing is important, especially in agriculture. A hailstorm striking a wheat field a few weeks before harvest can have a different consequence than the same storm striking shortly after planting. Now, it's important to remember this is not a forecast for every individual thunderstorm. I'm just talking about probabilities here. As I've mentioned many times, the atmosphere is incredibly complex. Regions that have experienced hail for years are still going to experience it. But local weather patterns may begin to change. And what this research is suggesting is that the background environment supporting the hail may be slowly reorganizing itself. So what does this mean for you? I think the most important lesson is that weather risk isn't just about intensity. It's also about location. In the Great Plains, where severe weather is common, hail is simply part of the environment. Farmers, insurance companies, and builders expect it. Nobody likes it, but nobody's surprised by it either. People understand that living in this part of the country means accepting a certain amount of hail risk as part of everyday life. The challenge highlighted by this research is that the geography of the risk may be changing. If hail-favored environments begin shifting poleward, some communities can find themselves dealing with a hazard that historically wasn't a major concern. Our infrastructure is often designed around weather we expect, not exactly the weather we may experience decades from now. Think about something as simple as a roof. Building codes in different regions account for different risks. Some places prioritize snow loads, others prioritize hurricane-force winds. That same principle applies to hail. Communities that rarely experienced damaging hail in the past may not have invested heavily in hail-resistant materials or forecasting programs or mitigation strategies. And of course, insurance works the same way. Insurance companies depend heavily on historical records to estimate future risk. We discussed this in a previous episode. But one of the recurring themes we've explored is that climate change can make the future look different from the past. When that happens, the historical record becomes a less reliable guide. We've seen this conversation emerge around flooding, hurricanes, droughts, and wildfires. This research suggests that hail may be another example of that broader pattern. And there's another interesting challenge. Many of the technologies we are building to help combat future climate, such as solar panels, upgraded electrical substations, new transmission lines, wind turbines, and electric vehicles, even more densely packed cities clad in glass. All of them exist in an atmosphere, which means they're all exposed to whatever weather the atmosphere decides to deliver. Historically, engineers design infrastructure for the risks they know. If you're building in Minnesota, you think about snow and ice. If you're building in Florida, you think about hurricanes. If you build in the Great Plains, you think about tornadoes, wind, and hail. But what happens when the geography of risk begins to shift? Imagine investing millions of dollars in a solar installation in a region that has rarely experienced severe hail. The panels may be engineered to withstand the weather that location has historically experienced. The insurance models may be based on decades of local observations. The maintenance plans may assume that destructive hail is a relatively rare event. Then, over time, the atmosphere changes and the probability of severe hail begins increasing. Suddenly, the assumptions used to design that system may no longer match the environment in which it operates. The same challenge applies to electrical infrastructure, vehicles, homes, buildings, and countless other systems that were built using yesterday's climate statistics. And that's one of the broader lessons emerging from climate science. We are changing not only the physics of the atmosphere, but also the probabilities and risks concerning where certain hazards are most likely to occur and when they are most likely to occur. For communities that have long dealt with hail, adaptation is already part of life. Building materials, insurance practices, warning systems, and personal experience all help reduce vulnerability. But for regions where severe hail has historically been uncommon, the learning curve may be much steeper. A hailstorm depends on a very specific balance of ingredients. It needs heat, it needs moisture, it needs instability. It needs freezing temperatures high above the ground, and it needs all of those ingredients to come together exactly in the right place and exactly the right time. Climate change isn't eliminating these variables, but it is changing them. As a meteorologist, that's what I find so fascinating about this. The softball-sized hailstone that shattered the window of my research van all those years ago left an indelible impression on me. It taught me that no matter how knowledgeable or experienced you are, the atmosphere can throw you curveballs. That massive stone was a product of a very specific set of atmospheric conditions. I thought I was witnessing a rare, localized spectacle of nature's raw power, a Great Plains anomaly. But the question scientists are now asking is how similar conditions may change in the decades ahead. While that doesn't mean such events will become more common, it does mean if you live in an area that rarely experiences hail, you may have to keep an eye on the sky more often in the future. I'm Dr. Mack, and this has been the Climate Translation. If you have a question about the climate you've been too afraid to ask, or if you have a differing opinion, I want to hear from you. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.